Okay, for today, we'll be looking at June 2022 P13. Let's have a look at the first question. For the first question, which pair of quantities are physical quantities? If you look at each of the answer choices, in A, charge and ampere, ampere is actually unit. For B, efficiency and kilogram, kilogram is actually a unit. For C, Pascal and strain, Pascal is actually a unit. So that will leave us with only answer choice D. For D, period is physical quantity. Potential difference is also physical quantity. So the answer is going to be D here. Now, when you're talking about ampere, ampere is the unit of current. And then for kilogram, is actually the unit of mass. And then Pascal is actually the unit of pressure. Okay, so this column here is unit, and then this column here is actually physical quantity. All right, then let's move on to question 2. In question 2, which list of unit prefixes decreases in magnitude from left to right? Now, when we talk about prefixes, we know they are used for very large values or very small values. So let's just write out all the prefixes that we know. If this one represents very large values, 10 power 3 would be kilo, 10 power 6 would be mega, 10 power 9 would be giga, and then lastly 10 power 12 would be tera. These are for very large values. But what about for very small values? So if we are talking about very small values, we look at it like this. For very small values, you would have 10 power minus 1 for deci, 10 power minus 2 for centi, 10 power minus 3 for milli, 10 power minus 6 for micro, 10 power minus 9 for nano, and lastly 10 power minus 12 for pico. Okay, so these are actually for very small values. But the question wants in decreasing order of magnitude. So when they want it in decreasing order of magnitude, you're basically looking at it from here to here. Okay, so this is where you would say they are in decreasing magnitude. All right, so let's look at the answer choices one by one again. For A, centi, deci, and milli, this is actually wrong because centi and deci are in the wrong order. And then for B, you have deci, milli, and centi. This is also wrong because milli and centi are in the wrong order. For C, you have pico, kilo, and milli. This is wrong because it is actually in increasing magnitude. You want decreasing magnitude here. So the only answer choice should have been D, but let's just check whether it's correct. You have kilo, milli, pico. This is actually correct because you see on the left hand side here, kilo is here, going to milli, and then going to pico. Okay. For question 3, the drag coefficient CD is a number with no units. It is used to compare the drag on different cars at different speeds. CD is given by the equation CD equals to 2F over V power N rho A, where F is the drag force on the car, rho is the density of the air, A is the cross-sectional area of the car, and V is the speed of the car. What is the value of N? So for our case, when we want to do a unit analysis here, it's best to make the variable that we are interested in as the subject of the equation. So let me just write it at the top right-hand corner here. CD is actually 2F over V power N rho A. We make V power N the subject of the equation here, giving us 2F over CD rho A. Then from here, we can say that the unit of V raised to the power of N is equal to the unit of force divided by the unit of rho and A. Now, why is it that we don't bother about CD here? It's because they already mentioned that CD is a number with no units. So since CD here has no units, it is actually ignored. Okay, so let's just proceed with the unit analysis. For force, the unit is kg meter per second squared. For density is kg per meter cube. And then for area is actually meter squared. And then you're talking about the unit of velocity itself is actually meter per second, now raised to power n. If you now try to solve the equation or simplify it, you will eventually get this meter per second power n. The kgs will cancel each other off. And then the bottom is meter power minus 3 times meter power 2. This is actually going to give you meter negative 1. Meter divided by meter negative 1 will give you meter power 2. And then second negative 2 remains as it is. So this expression here, you can actually try to simplify it, where this one is meter per second raised to the power of 2. So now you try to make a side-by-side comparison of the equation, you can actually see that this power n is actually power 2. So n is equal to 2. The answer is B here. All right. So for question 4, you have a micrometer screw gauge that is used to measure the diameter of a small uniform steel sphere. The measurement of the diameter is 5.00 millimeter plus minus 0.01 millimeter. What is the percentage uncertainty in the calculated volume of the sphere using these values? When you are talking about a sphere, you know that its volume is equal to 4 over 3 pi r cubed. In our current question, the radius isn't given, but rather the diameter is given. So it will be a good idea to just change this equation so that it has diameter inside. So this now becomes 4 over 3 pi d over 2 cube. Remember that radius is actually half your diameter value. So now we have 4 over 3 pi d cube over 8, which in turn simplifies to 1 over 6 pi d cube. So when we want to get uncertainties out of this equation, we know that this equation form will actually give us fractional uncertainty of volume equals to 3 times the fractional uncertainty of the diameter. So now if you sum in the values, we get 3 times of 0.01 divided by 5.00, we will get 0.006. Now, to get percentage uncertainty that is required by the question here, percentage uncertainty is actually our fractional uncertainty multiplied by 100%, giving us 0.6% here. Our answer will be C. Now, what if you had wanted to use this equation with the radius instead? You can do so, but you will need to make some adjustments. Remember that in your question, they mentioned that D is 5.00 plus minus 0.01 millimeter. And we know that radius is actually half your diameter value. So right now, when you want to get the radius, it's actually 5.00 plus minus 0.01 divided by 2, giving us 2.500 plus minus 0.005. When you want to get the radius value, you would divide the diameter by 2, but you would also need to divide the absolute uncertainty of the diameter by 2. You need to divide both values. Only then would your calculation for uncertainty be correct. So now if volume is 4 over 3 pi r cubed, the fractional uncertainty of the volume would be equals to 3 times the fractional uncertainty of the radius. If you put the values in now, you get 3 times of 0.005 divided by 2.500, giving you 0.006. So you want to move on to find the percentage uncertainty now. It will actually be 0.006 times with 100%, giving you 0.6%, which is actually the same answer as before. You can use either method, but as a rule of thumb, it will be better to just use an equation that already has the variables from the question inside. You see, like when I try to find the volume and I use 1 over 6 pi d cube, I could have just straight away used the values from the question without having to do any further calculations. So this method is actually more straightforward in a way. Now, if you look on to question 5, forces of magnitudes 2 Newton, 4 Newton, and 7 Newton combine to produce a resultant force. The magnitudes of the three forces are fixed, but the forces may act in any direction in the same plane. What is not a possible magnitude of the resultant force? So we can just consider all the forces as acting along the same line. So when they all act along the same line, the easiest example to consider would be all of them acting in the same direction. So you have the 2 Newton, the 4 Newton, and the 7 Newton all acting towards the right. So 2 Newton here, 4 Newton, and then 7 Newton. You will get a resultant of 13 Newton pointing towards the right too. So this resultant force is actually the maximum possible. And then if you consider one of the forces acting in the opposite directions, say you have the 2 Newton force and 4 Newton force acting towards the right, but your 7 Newton force acts in the opposite direction towards the left, you now have 2 Newton, 4 Newton, and 7 Newton. Your resultant is going to be 1 Newton acting towards the left. So this 1 Newton is actually the minimum possible resultant force. Now, what about the other resultant forces listed inside the question? Is it possible for you to get them? It is possible if you consider the forces as acting in different directions. So an easy example for us to consider would be just to think about it as this. You have the 2 Newton force and 4 Newton force acting towards the right. This will give us a resultant of 6 Newton. And then you consider the 7 Newton force as acting perpendicular to the first two forces. This is your 7 Newton. If you recall what you learned about finding resultant forces, you learned that if you were to draw the vectors from head to tail in this manner, any gap remaining is actually your resultant. The length of the gap is the magnitude, and the direction will be from your initial point to your final point. So over here now, your resultant will actually be given by this red colored arrow. This is your resultant. And at the same time, you would notice that this forms a right angle triangle, where in your case, theta is 90 degrees. So you can actually find out the resultant by treating it as the hypotenuse of your triangle. So your resultant will actually be given by square root of 6 square plus 7 square, giving you 9.2 Newton. And then here, you can also notice one thing. If you were to decrease the angle theta here, what do you suppose will happen? If angle theta here is decreased, the blue colored arrow here representing your 7 Newton would actually shift positions to here, here, or even here. Now, when it does that, notice what happens to the length of your red colored arrow, which is your resultant. It will become shorter and shorter, meaning to say your resultant is becoming lesser and lesser. So it will be correct to say that when your angle theta decreases, your F net would actually drop. Okay, so consider this. If you were to keep on decreasing your angle theta, you would eventually come to a value of 8 Newton and 5 Newton that is listed inside the question here. Say, for example, if you were to decrease your angle to, say, angle alpha, you will still have your 6 Newton here, and then your 7 Newton would be something like this now, where your angle here is now, say, alpha. Your resultant would have decreased from 9.2 Newton from above to, say, maybe 8 Newton. And then if you continue to decrease your angle even further, you might end up with something like this, where you have your 6 Newton here, and then your 7 Newton is tilted even lower like this, so that your resultant becomes even shorter still. You could end up with, say, maybe 5 Newton here for an angle of, say, maybe beta. So you look at the answer choices right now, it is possible for you to get 13 Newton, 8 Newton, and 5 Newton. It is just simply not possible for you to get 0 Newton. Therefore, the answer is A. Now, if you consider the last case here, where you keep on decreasing the angle all the way to 0, you're really going to end up with something like this. Okay, so it is really not possible to get 0 Newton. And then you look at question 6. This will require a fair bit of explanation. Two projectiles X and Y are fired into the air from the same place on level ground and reach the same maximum height, as shown in the diagram below. Projectile X is fired vertically upwards and projectile Y is fired at an angle to the horizontal. Air resistance is negligible. Which statement is correct? So let's first consider in detail what happens for each of the projectiles. Projectile X would move with a straight line like this. Projectile Y will move in a parabolic curve like this. So if we just look at projectile X first, before we go through that, recall that they mentioned that your projectiles were both projected from the same place on level ground and reach the same maximum height. So let's just first draw two lines to represent the starting point, which is the same level ground, and the maximum height. So these two lines represent your starting point and your maximum height. For path X, your projectile was projected upwards with a certain velocity. So it will go up, reach the maximum height, and then move back down until it hits the ground again. All right. So here, what can we say about path X? Now, since path X is just fired vertically upwards and then it moves back down, it's only vertical motion. So in our case, you only have vertical velocities to consider. Now, as it moves up, we will say that it is actually slowing down because the direction of its motion is opposite to the direction of the acceleration that it experiences. In our case, the acceleration is actually equals to g. How do I know that? It's because of the statement here saying that air resistance is negligible. When you have this statement here, it already tells you that weight is the only force. Therefore, A will be equals to G and is constant. So let's go back to path X here. We know that when it goes up, it will slow down because the motion is opposite to its acceleration. But when it goes back down, it will start to speed up. Because in your case now, the direction of motion is in the same direction as the acceleration. Okay, so if you try to visualize the velocities going up and velocities going down now, this is what you expect to see. So let's just indicate a few points on your path X. This one, this one, this one, this one, and this one. So as your object goes up, its velocity will get progressively smaller because it is slowing down. So your arrow will become smaller and smaller until it is 0 at the maximum height. This point here is your maximum height. Okay, then when it starts to move downwards, your velocity will start to get larger and larger again because you're speeding up. So your arrow length will become larger and larger. Okay, so that's what's happening for path X here. Then if you look at path Y, the projectile was projected upwards at a certain speed at an angle to the horizontal. It would have moved upwards to reach the maximum height, and then it will fall back down and hit the ground again in a manner similar to this. So if it was projected upwards at an angle of theta, it will also hit back the ground at an angle of theta. Okay. Now, because you are moving in a parabolic curve like this, there's actually a combination of horizontal and vertical motion. You would have horizontal and vertical velocities to consider. So now, when you're talking about path y would have both vertical and horizontal velocities. Now, specifically when air resistance is negligible here, there are two things that you can say. The first one being that you would have constant horizontal velocity. And then the second one being that you would have constant vertical acceleration. Okay. Now, if you look at the starting position, the projectile was projected upwards at a certain speed at a certain angle to the horizontal. So that speed there can be resolved into horizontal and vertical velocities. Now, assume that this speed is v. If you were to resolve it into the horizontal velocity, it will look something like this. If you were to resolve it into the vertical velocity, it will look something like this. Okay, so let's consider what subsequently happens to these velocities when your object moves up to the maximum height and then moves down to the ground again. For the first half of your motion from the starting point to the maximum height, the projectile is actually slowing down. Because here, the direction of our motion is upwards, but the direction of our acceleration is downwards. They are in opposite direction, so it will therefore slow down. But then, after that, from your maximum height to the ground again, it would actually be speeding up. Because here, the direction of our motion is downwards, and the direction of our acceleration is also downwards. They're both in the same direction, so therefore they will speed up. Okay. Now, the horizontal velocities itself would actually remain the same throughout, because here it was already mentioned you should have constant horizontal velocity. So Vx remains the same throughout the motion of the projectile. The magnitude would not change. But on the other hand, when you consider the vertical velocities, because as it moves up, it is slowing down, the vertical velocity will keep decreasing. So the arrows here that you see representing velocity will keep getting shorter and shorter until it reaches 0 at maximum height. So maximum height is this point here. Okay. So once you reach maximum height, your vertical velocity is 0, but from the maximum height all the way to the ground again, because you are speeding up now, your velocities will start to increase. So the length of this arrow will keep getting longer and longer and longer. All right. Now let's look at the first answer choice. They say that X and Y are at rest at their maximum heights. Is it correct to say that X and Y is at rest at the maximum height? This is actually not true, okay? For projectile X, it would actually be at rest at maximum height because it only consists of vertical velocities. Just now I mentioned that as your projectile moves upwards, it will actually slow down. So the vertical velocities here would keep decreasing until it reaches 0 at maximum height. So at maximum height, the vertical velocity is 0, and there's no horizontal velocity to consider. You can actually say that at maximum height, it is at rest. But you cannot say the same for path Y because you have both vertical and horizontal velocities to consider. The vertical velocity will keep decreasing to 0 at maximum height because you are slowing down as you're moving upwards. Now, at maximum height, although your vertical velocity is 0, you actually still have horizontal velocity there because you're supposed to have constant horizontal velocity throughout your motion. So your object is actually still moving there. you cannot say that it is at rest. That's why A here is wrong. Now for B, X and Y are fired with the same speed. If you look at the term that they use, they're using speed right over here. There is a difference between speed and velocity. Speed is a scalar. You only need to consider the magnitude. But when you're talking about velocity, velocity is a vector. You need to consider both magnitude and direction. Now, in the context of our question, speed is the resultant velocity at a point. When speed is the resultant velocity at a point, it means that it is actually the resultant of our horizontal and vertical velocities. And this always acts tangent to the path at the point that we consider. For projectile X, the speed is really just the vertical velocities because it was already mentioned here that it only consists of vertical velocities. But for projectile Y, you will need to consider both the vertical and horizontal velocities. So in our case, the speed here is actually these arrows right over here. It is the resultant of your horizontal and vertical velocities, and it will be tangent to the path at the point that you consider. Let me just write it over here. When you're talking about speed at X, it is actually the vertical velocity only. But when you're talking about the speed at Y, it is actually the resultant of your horizontal and vertical velocity. Now, the next thing you want to consider is this. The question mentioned that you had the same starting point and maximum height. So the significance of this is that it will actually tell you that you have same vertical distance traveled. So this being your starting point and this being your maximum height, you can actually already see from here that your vertical distances are actually going to be the same. All right. So here you will be correct to say that you have same vertical distance travel. And then at the same time, because it was already mentioned to you that air resistance is negligible, I mentioned to you that your acceleration will be equals to g and it will be constant here. Another thing you can actually say from here is this. Both projectiles would be having the same downward acceleration. So both projectiles are actually experiencing an acceleration equal to the gravitational acceleration, which is always directed downwards. Next, you consider this. If both projectiles were going outwards from the starting position to the max height, both projectiles will actually be slowing down at the same rate. And then similarly, when both projectiles started to move downwards from the max height back to their starting position, they will actually also be speeding up at the same rate. When you consider what happens to both projectiles when they're projected from the starting position to the maximum height, they will both be traveling the same vertical distance and they will both be slowing down at the same rate. This will actually tell you that both projectiles actually have the same initial vertical velocity. For example, in projectile X, you could have an initial vertical velocity of 10 meters per second, same as that of projectile Y, so that when they're both projected outwards, they slow down at the same rate to reach the same maximum height. But for projectile y itself, there is still some horizontal velocity here to consider. Say maybe it is 15 meters per second. Now, speed being the resultant of your horizontal and vertical velocities would mean that your speed here is actually 18 meters per second. This is your speed right now. But when you consider for projectile x, because it only consists of vertical velocities, this 10 meters per second is actually your speed. Now you can see that the speeds are actually different now. For x is 10 meters per second, for y is 18 meters per second. That's why we cannot say that x and y are fired with the same speed. For c, x and y take the same time to return to the ground. Earlier, it was mentioned that both projectiles would travel the same vertical distance and that they will slow down at the same rate when going up and speed up at the same rate when going down. There's one conclusion that you can actually draw from here. That one being that time taken to move up and down for both projectiles are the same. Therefore, the total time taken for both are also the same. So answer choice C is actually correct. X and Y would take the same time to return to the ground after you project it upwards. Now for projectile Y, you may be wondering, because there's horizontal motion involved, shouldn't the timing also be affected? Now the answer is no. For projectile Y, the object moved up and then down, and at the same time, it was also moving horizontally towards the right. Now, one thing that I would have mentioned a number of times in kinematics was this. The time taken to move vertically to a point is the same as time taken to move horizontally to the same point. Now, what do we mean by that is something like this. If it took you 20 seconds for you to move up and down, it will also be taking you the same 20 seconds for you to be moving from left to right. So in other words, T vertical is the same as T horizontal. Okay? Now, before we move on to the next question, let's look at the last answer, choice D. X and Y travel the same distance. Now, this one will be pretty straightforward for us to answer. Projectile X travels vertical distance only, but projectile Y travels both horizontal and vertical distance. So just now, we already made a discussion saying that both projectile X and Y will be traveling the same vertical distance. But for projectile Y itself, there is also horizontal distance traveled. So Y travels more distance than X. Therefore, the answer cannot be D. They cannot be traveling the same distance. Okay, question 7 should be a lot easier to understand now. It's always kinematics that's a bit difficult. Okay, now for question 7, you have a small glider that moves along a horizontal air track as shown. At each end of the air track, the glider has a perfectly elastic collision with a fixed buffer. The glider moves at constant speed between collisions. Which graph represents the variation with time t of the velocity v of the glider as it moves between two buffers? So there are some keywords here that you need to identify. The first one is that this one is an air trap. And then the second one is that this is a perfectly elastic collision. So these two are some keywords to take note of. Now, which of these is actually your correct velocity time graph? The one that should be correct here is actually D. Okay, but how do you know it's going to be that shape? You just imagine something like this. If you have your buffer, I try to draw it right over here. This is, say, your buffer at both ends. And then you have your glider that's moving towards this side with velocity v. Because you have perfectly elastic collision in the first place, whenever you see perfectly elastic collision, the first thing that will come to mind is this. Your relative speed of approach is equal to relative speed of separation. This is one. And then your sum of kinetic energy before collision is equal to the sum of kinetic energy after collision. These are the two things that are normally associated with perfectly elastic collision. So specifically, you look at the first criteria, relative speed of approach equals to relative speed of separation. If you look at the buffer at the right-hand side, your object is moving towards it with velocity v, but because the collision is elastic, it hits with velocity v, it will also rebound with velocity v, so that your relative speed of approach and separation still remains at v. You see, your buffer is considered to be at 0 meter per second. It doesn't move. So if you consider your relative speed of approach here is just v. But if the collision is to be elastic, your relative speed of separation must also be v. That's why here I can say it hits with v and then it rebounds with v. Okay, so it goes away from your right buffer. You move with velocity v again until it hits the left buffer. How do I know it will move with velocity v after rebound? Is because of this. Because you see, they mentioned that you have an air trap. It's just a layer of air beneath your glider. So no friction to oppose motion. No friction to oppose motion. Therefore, object moves with constant velocity. You can think of it as due to Newton's first law, an object will travel with constant velocity unless a resultant force acts on it. In your case, it's just an air track, no friction to oppose the motion. Object will just continue moving with constant velocity. Maybe I should write another statement here. It's an air track, no friction to oppose motion, no resultant force. Okay. Object moves with constant velocity since there is no resultant force. Since there is no resultant force. Okay, there's no F net. You do not have any force pushing the glider forward. You do not have any friction opposing the motion of the object. There's no net force. So you move with constant velocity. This one can also be implied from Newton's first law. Okay, so you move with constant velocity. And then after that, same thing, it will hit the left-hand buffer with velocity v, and it again will likewise rebound with velocity v, because same thing as before, the collision is elastic. Relative speed of approach is v now. Relative speed of separation would also be v. Okay, so that will immediately tell you on and off your velocity should remain the same. You see, this one and this one, they are the same. Your velocities is exactly the same. Okay, but then after that, you can see that, yeah, the velocities being the same, that one is answer choice C and D also, right? But why is it going to be D, not C? It's because of what I just mentioned to you. because you have no friction opposing your motion, you have no net force, your object will continue to move with constant velocity, isn't it? So a consequence of this is this. You see, your distance between your air track remains the same throughout, right? You see, this is the distance between your, not the air track, the distance between your buffer. This is the distance between your buffer, right? So if I tell you your speed is constant, and I also tell you your distance between the buffer is constant, the distance between buffer is constant, this will automatically tell you the time taken to hit buffer is also constant. See, this is the time to hit the buffer. Both of them, I mean, all of them are constant. This one could be you hitting the first buffer. This could be you hitting the second buffer. So the time between your buffers is actually constant here. Okay, so time taken to hit buffer is also constant. This is why the answer is D, not C. If you C, you'll notice that the time to hit your buffer is getting lesser and lesser and lesser. This cannot be the case here. You can only say so if you are suddenly you can only say C if your glider is suddenly speeding up. So if it's speeding up, then that will explain why your time taken to hit the buffer is getting shorter. All right. So that's question 7. Then you go on to question 8. So for question 8, they mentioned that a car accelerates from rest. The graph shows you the variation of the momentum of the car with time. What's the meaning of the gradient of the graph at a particular time? So this one, I think, is pretty straightforward. Is momentum with time. You know that force is rate of change of momentum, which is actually the gradient of your PT graph. So they're asking you the gradient of your graph, right? They're asking you about the gradient of your momentum time graph. This one is actually going to be your resultant force. The resultant force on the car. Okay? The gradient here of your momentum time graph is the resultant force on your car. So that's okay. Now for question 9, you have a ball that's dropped onto horizontal ground and bounces vertically upwards. When the ball is in contact with the ground, these are the following forces that act. You have weight W of the ball, contact force P exerted on the ground by the ball, and then the contact force N exerted on the ball by the ground. So when the ball is in contact with the ground, the ball is momentarily stationary. At this instant, which relationship is supposed to be correct here? So momentarily stationary here would just simply means that velocity is 0. Okay. And then from here, they want you to find out the relationship between the forces that have been listed here. Okay, the W and N here are forces that act on the ball. Just to differentiate certain things first, the weight and the normal reaction force N are forces exerted on the ball. The P is not the force that's being exerted on the ball. It is the force that's being exerted on the ground. Okay. So just to take note of these forces here. So here, you imagine this, if your ball hits the ground, after a while, it will start to rebound upwards, right? So here, when they tell you that the ball is in contact with the ground and then the ball is momentarily stationary, after this point here, your ball will start to rebound upwards. Okay, at this point here, you actually already have a net force acting on your ball. That net force is actually directed upwards. Okay, it's because you have this net force acting on your ball that your ball is able to bounce outwards later on. Okay, your net force is directed upwards here. So you apply F net equals to MA for the ball itself. What is my net force? My net force is actually going to be N minus W Then after that, you shift the n towards the left side, n will actually now be f net plus w. So if you look at this equation itself, your w must be added with your net force to give you n. So this tells you that n is already more than w itself. So your answer is actually D. Okay, that's how you do this particular question. You won't consider the rest of the answer choices, like let's say A and B, because as I mentioned to you, P is actually not the force on the ball, it's actually the force on the ground. So I won't really consider anything related to P here. I only consider C and D. But when it comes to these two, I should have realized that the ball is actually at the point of bouncing up. Maybe I should rewrite this. When your ball is momentarily stationary, you can also think of it as at the point of bouncing up. Therefore, F net is upwards. Yeah, that's the significance of that statement there. So if I apply F net to my question now, this is what I get. All right, so that's for this particular question. Then after that, there should be another question, question 10. Yeah, so we'll move on to question 10. Now in question 10, they mentioned that a person stands on the edge of a high cliff that is next to the sea. The person throws a stone vertically upwards and then air resistance acts on the stone. This stone eventually hits the sea. Which velocity time graph best represents the motion of the stone from when it is released until it hits the sea? So just imagine this. This one is your cliff. You have a person standing right over here and he threw a stone up. So the stone went all the way up, going from here all the way to maximum height. And then after that, the stone went back down and hit the sea right below. Okay, it hit the sea right below here. So this part here is maximum height, right? Now, there's one thing here that you can actually just straight away identify from here. Your motion here consists of two different directions. You can see that this one here is motion up, and then this one is motion down. Okay, so because your direction of velocity depends on direction of motion, direction of velocity depends on the direction of motion. If you're going up, your velocity is upwards. If you're going down, your velocity is downwards. So one thing here that you can actually say here is this: since there are two different directions, there are two different velocity directions. Okay, because you have two directions here, you have two different velocity directions. Therefore, there is positive and negative velocity. Okay, you will have positive and negative velocity in the first place. So here you can probably say this one is velocity in one direction when you're going up, and then when you're going down, you have velocity in opposite direction. Okay, in other words, you're just going to have positive and negative for your velocities. So if you look at your graphs, C and D is automatically out because you see there's no negative velocity. If you have two different motion direction, you will have two different velocity direction, hence you have positive and negative velocity. So C and D is out. It's just saying that you only have one direction of velocity. You're really only just moving in one direction. This is wrong currently. So that leaves you with only answer choices A and B. So which one should be the correct one? Actually, it's actually supposed to be B. Okay, but why do I say B is the correct one in the first place? Is mainly because of the fact that you have air resistance. So you consider this now, when you are moving up, you are actually slowing down also, right? And then when you're moving down, you are actually speeding up. Okay, and let me just rewrite it somewhere here. When you're going up, you will slow down. When you're going down, you will speed up. Okay, so because you have air resistance here, one of the things that will happen is something like this. You see, if you're going upwards, this is the direction of your motion. Let me just separate this thing out. When you're moving upwards, your weight is acting downwards, and then after that your air resistance is opposing your motion, because you see this is the direction of your motion when you're going upwards. So you have weight acting downwards, that is a given, but you also have air resistance opposing your motion. It will be directed downwards. Okay, now if you apply resultant force equation here, F net would actually be W plus R. Okay, let's just assume that this is the direction of your acceleration. Now, because you're slowing down as you go up, this one is something that you know, and air resistance being proportional to speed, this is one relation that you should have known. If your speed is decreasing because you're slowing down, your air resistance drops. So as a result, your air resistance dropping, this would mean that your F net will drop, your acceleration will drop. A is not constant. Okay. So this one is something that you should know when you're moving upwards. What about the case where you're moving downwards? When you're moving downwards, your object is having a motion downwards here like this. Your weight is again directed downwards, but your air resistance this time is opposing your motion, so it's directed upwards. Then your direction of acceleration here is again downwards. If you apply equation F net here, it will be W minus R. Now in your case, you know that as you move down, you will speed up. So here, what you can kind of say is this: your V increase, your R increase. So when your R increase, again, your F net drops, your acceleration drop. A again is not constant. Okay. Now, how do I know, why do I say both F net is still dropping? You can actually kind of see from here, actually. This one here, just not weight is fixed, right? And then R is dropping, so F net will drop. But then for the second case, W is also fixed, but R is increasing. So a fixed value is subtracting a larger value. Now, obviously, your net force will drop. Okay. So that's why I can say both cases, F net is actually dropping, which in turn results my acceleration is drop, which in turn results both acceleration decreasing here. Okay. And then from here, one thing that you can actually do is to relate the gradient of velocity time graph and acceleration. You know acceleration is rate of change of velocity, right? It's actually the gradient of your VT graph. So if A is decreasing, your gradient of your VT graph should be decreasing, which is actually what you're seeing here. Okay, you see your gradient is actually decreasing in value. This is the correct one. It's showing to you that your acceleration is not constant. It's showing to you that your acceleration is changing. Okay, so answer here is B. And then one thing I should probably mention to you here is this one is you moving up. The negative velocity here is you moving up. The positive velocity here is you moving down. Okay. Now, you actually don't need to do this kind of analysis in the first place. All right. There's one straight answer you can probably just use in order to get the answer B. Because there's air resistance, straight away I know A is not constant. Okay, there's a straightforward way to answer this question. The moment I see air resistance X on the stone, I already know A is not constant. That's why here I can straight away cancel A. Okay. You don't need to do the analysis on the right. It's actually pretty time consuming if you want to do that. Now for question 11, let me just clear this thing out. For question 11, you have skaters of mass 80 kg and 40 kg that move directly towards each other and collide. Before the collision, the heavier skater is moving to the right at the speed of 2 meters per second, and the lighter skater is moving to the left at the speed of 1 meter per second. After the collision, the heavier skater moves to the right at the speed of 0.8 meters per second. What would be the relative speed of separation of the two skaters? Okay. Now here they suddenly made mention of relative speed of separation here. Okay. There is no mention of this collision being elastic. Okay, when you guys were doing relative speed questions, all this while is always a case where you see the collision was elastic, right? Here, you cannot just simply assume that your collision is elastic. It was not mentioned anywhere in this question. You should not assume that the collision is elastic, because some people assume that your collision is elastic. They straight away find the relative speed of approach here, and then straight away say that relative speed of approach is equals to relative speed of separation, so therefore that's the answer. That is actually the wrong approach here, because here no mention of elastic collision. So it's probably better you just write it out somewhere. This one, do not assume is elastic collision unless otherwise stated. Do not assume as elastic collision unless otherwise stated. Okay, so don't assume it's elastic collision here. Don't simplify relative speed of approach and say it's equals to relative speed of separation. So here, what you need to do is you apply conservation of momentum. You know you have the heavier skater here of 80 kg, and then you have the lighter skater here of 40 kg. So the heavier skater is moving towards the right with a speed of 2 meters per second, whereas the lighter skater is moving at 1 meter per second. Okay, so after collision, what happens is that the heavier skater still continues moving towards the right, but at the lower speed now of 0.8 meter per second. So what about the lighter skater? Now the lighter skater, after collision with the heavier person, obviously would be moving towards the right with a certain velocity, which we are interested to find out right now. Okay, it is not reasonable to assume that the lighter skater will continue to move to the left after collision with the heavier guy. So it must be moving towards the right. So here, if you apply conservation of momentum, where you say sum of the initial momentum before collision is equals to the sum of the final momentum after collision, you should get this value, 80 times 2 minus 40 times 1 equals to 80 times 0.8 plus with 40V. So that your V now is going to be some particular value. This one, let me find out the value here. The value is going to be 1.4 meter per second. Okay, this one is the velocity of the lighter skater after collision with the heavier skater. So here the question wants you to find the relative speed of separation. So when you want to find relative speed, it will just be higher speed minus lower speed if both objects move same direction. But if you're talking about objects that move in opposite direction, relative speed is actually the higher speed plus the lower speed. This one is if both objects move opposite direction. Okay, so in your case here, you have a case where both objects, or rather both skaters, move in the same direction. So you will be using this equation instead. Okay, your relative speed, just take the higher speed minus the lower speed, it will be 1.4 minus 0.8, giving you 0.6 meter per second. So your answer here should have been A. Okay, so that's for this particular question. Now in question 12, which statement describes the two forces in a couple? This one kind of relates to you having remember what is the definition of a couple. So let's just write it out. So what is the definition of a couple in the first place? A couple is a pair of equal but opposite forces separated by distance. Okay, and then another thing to know about couple is that couple only produces moment but no resultant force. Couple only produces moment but no couple produces resultant moment but no resultant force. It's better to write it like that. Couple produces resultant moment but not resultant force. It's because it's something like this. Because we say couple is a pair of equal but opposite forces separated by distance, you are going to get something like this. This one is force F, and then this one is force F, separated by a particular distance, D. So let's just say that I have a pivot right over here. Now, in terms of whether there's any resultant force, you can actually see that this F going up is cancelled by the F going down. So here, resultant force is just 0. But then when you consider whether there's any resultant moment, say you pick this center point here as your moment, you pick this center point here as your pivot, your forces will produce a moment. The force on the left will give you a moment clockwise like this, and the force on the right will also give you a moment clockwise like this. So both of them are in the same direction. They add up to give you a resultant moment. So this one here, the resultant moment is not 0. There is resultant moment here. Okay, so you look at the answer choices. They act in the same direction. This one is out. It must be opposite direction. They act through the same point. This one is also out. If they act through the same point, that means there's no separation between them. There's not a couple. You must have separation between them. You must have some distance between them. Okay. They produce 0 resultant force. This is actually correct. They produce 0 resultant moment. This one is wrong. Okay. So the correct statement here is actually C. Then if you're okay with that, then I move on to question 13. The rest of these questions are pretty straightforward. It's just the beginning part that was a bit difficult. Now, a straight line is fixed to a wall by a metal rod and a cable. Which vector triangle could represent the forces acting on the end of the rod at point P? So this one, the first thing to remember is that forces in equilibrium always forces in equilibrium form closed vector diagrams. Forces in equilibrium form closed vector diagram when drawn from head to tail. Okay, when drawn from head to tail. Whenever you have forces that are in equilibrium, they must form a closed vector diagram the moment they're drawn from head to tail. So they want you to identify the forces acting at point P here. You can identify two forces already there. You would have the weight of the lamp. You will have the tension exerted by the cable. So here they again ask you to identify another unknown force acting on the rod. They ask you to identify the forces acting on the end of the rod at point P. So there's another force here acting on the rod at point P. Is it going to be a force in this direction or a force in this direction? Which one should it be? That's the issue here. Should it be pointing towards the right or should it be pointing towards the left? So this one can be solved if you were to draw your two forces here from head to tail first. If you draw it from head to tail, you will get W like this, you will get T like this. This is W, this is T. If you are supposed to form a closed vector diagram or closed vector triangle here, the forces must be drawn from head to tail in the first place. So the only way that this one could be a closed vector diagram when drawn from head to tail is if the forces is drawn like this. This is the direction of your force F. So the correct answer would have been D. Okay? It cannot be this direction because you draw it like this. This is not drawing from head to tail already. When drawn from head to tail, the head of one vector must meet the tail of the other vector. Okay? So that's for this one. Then you move on to question 14. Hey, sorry. Yeah, move on to question 14 here. Okay, for question 14, they mention an unknown mass and a 1 kg mass are fixed at opposite ends of the bar. The bar has negligible mass and a length of 30 centimeter. The bar balances when it is supported by a pivot placed 20 centimeter from the unknown mass as shown here. What is the unknown mass here? Okay, so here they make your life easier already. They say this one is your pivot. And then they tell you there are two masses here. This one would have a weight of say m times g. This one would have a mass weight of 1 times g. Okay. Maybe I just rewrite it properly for you. Okay, this one is weight 1 equals to mj. This one is weight 2 equals to 1 times g. Okay, so what is the unknown mass? They want this particular mass here. So in your case, they already told you the bar balances. That already tells you that clockwise moment equals anti-clockwise moment. So the mass on the left-hand side gives you counterclockwise. The mass on the right-hand side gives you clockwise. So from there, you also still need to identify the perpendicular distances. For your clockwise moment, this one will be 1 times 9.81 times your perpendicular distance of 10 centimeter, 0.3, change to meter. And then your counterclockwise moment would be m times 9.81. Okay, maybe it's better if I use a different color here. This one would be m times 9.81 times 0.2. This is your perpendicular distance. So eventually your M is going to be a value of 0.5 kg, which is actually 500 grams. So answer is B. Okay. So that's for this. Then I move on to question 15. Okay, now for question 15, they mentioned that you have a block of wood of density rho W that has sides of length A. The block is immersed in a liquid of density rho L. The top surface of the block is at the depth H below the surface of the liquid. The acceleration of free fall is G. What is the upthrust acting on the block from the liquid? So this one, they're just asking you about the upthrust. When you're talking about upthrust, this one would always come out for you. Upthrust is actually the weight of liquid displaced, which is in turn rho Vg. Okay, so certain things to note is that this rho is the density of liquid, whereas this W here is the volume of liquid displaced, but it's also equal to volume of object submerged. Okay, the V here is volume of liquid displaced, but it's also the same as the volume of the object that has been submerged inside the liquid here. All right, so here, if you want to get the upthrust, the rho here must be the density of the liquid, so it's rho L. The V here should be the volume of liquid displaced, but it could be the volume of object submerged too. So here you want to get the volume of object submerged. You take it from multiplying the sides together, because this is cube. This one is actually going to be A cube. Then multiply with your gravitational acceleration, you will get your answer as basically A, rho L A cube times G. Okay. So this one I just mentioned volume is actually A cube. Okay, so that's all right. Then question 16. For question 16, they mentioned this. A technical article about diesel engines expresses the energy available from diesel fuel as 41.8 megajoules per kg and as 34.9 gigajoules per meter cube. What is the density of diesel fuel here? Okay. So what you have in the first value here is actually energy per unit mass. Then the second value you have here is energy per unit volume. And then you're supposed to use these two values to find out the value of density. So to find out the value of density is probably better just to go back to the basics. Density is actually mass per unit volume. Now you can also say that density is energy per unit mass times with volume. Sorry, I did it the other way around, sorry. If you want to get density as mass per unit volume, it can be found by the products of two different ratios. Namely, you can say is mass over energy times with energy over volume. You can see from here that these two energies will cancel, giving you back mass per unit volume, right? So here you have these two given already inside your question. You will try to put them in. So in your case, you have you have energy per unit mass. Energy per unit mass of 41.8 megajoules per kg, right? This is actually the same as you saying that you have 41.8 megajoules over 1 kg. So here, mass over energy will actually be 1 kg over 41.8 megajoules. This is one. And then the next one is you having energy per unit volume. Energy per unit volume here will be 34.9 gigajoules. 34.9 gigajoules per meter cube, which is the same as 34.9 gigajoules over 1 meter cube. Okay, so you want to sub these two into your equation. Wait, now let me just write this. You want to sub these two into your equation above. So you sub them in, mass over energy would be 1 kg divided by 41.8 megajoules. So don't forget the prefixes. Then multiply with energy per unit volume. You get 34.9 times 10 power 9 divided by 1 meter cube. So eventually you get the answer as 835 kg per meter cube. So answer is actually A. Okay. So that's for this one. And after that, move on to question 17. For question 17, what is meant by the efficiency of a system? When you're talking about efficiency, it is really just the ratio of your useful energy to your input energy. If you had wanted to write it in terms of percentages, you would have multiplied with 100%. In your question here, your answer is supposed to be C. It is the ratio of the useful energy output from the system to the total energy input. The rest of the answer choices just don't make sense. Now in question 18, you have a car with 15,000 Newton traveling along a horizontal road. At one instant, the thrust force acting on the car from the engine is 12,000 Newton and the resistive force acting on the car is 3,000 Newton. The velocity of the car at this instant is 24 meters per second. What is the power output from the engine? Okay. Right, so just to recap a little what you guys learned for work, energy, power. When you're talking about work done, you know it's the product of force and distance moved in the direction of the force. There are a few conditions attached to this equation. This one, we will say is distance moved in direction of force. This is one condition attached to the distance here. And then for the force here, this one, the force is applied force, not resultant force. Okay. So when you want to use the equation, W is being the product of force times distance. There are some conditions to always remember. The distance must be distance moved in the direction of the force. The force must be applied force, not resultant force. Okay, don't ever use resultant force when finding work done. Okay, so if you move on to power, power was defined as rate of work done. Is W over T. Okay, so W is Fs divided by T, then this one will become F times S over T. S over T in turn will become equals to volume. Sorry, not volume. S over T will in turn become equal to speed. So P is equals to Fv. All right. So now, because your P is derived from work, and work is product of force times distance, the condition for F that you use here will be carried over for power. So this F that you use must be applied force, not resultant force. Cannot be resultant force. So when they ask you to find the output power from the engine here, you can use P equals to Fv, but the force that you use must be the thrust force from the engine. This is actually your applied force here. You don't go and take 12,000 Newton, multiply minus all 3,000 Newton, giving you 9,000 Newton and put it inside. This is wrong because this is actually net force. Okay, so don't ever use net force. Use the applied force. So in your case, you will use the value of 12,000 Newton multiply with your speed of 24, giving you a final answer of 288 times 10 power 3 watts. So it's 288 kilowatts. Change to 2SF, it will be 290 kilowatts. Okay, that's for question 18. So then I'll clear this one up and move to the question below. This one is on graph drawing. Now, in question 19, the diagram shows you the variation with a quantity y and a quantity x for objects in the uniform gravitational field. Now, when they tell you uniform gravitational field, this one already kind of implies to you G is constant, okay? So what could x and y represent here? So in your case, you notice that they mention kinetic energies and GPEs, right? So try to relate to the equations for GPE and kinetic energy. So in the first place, if I talk to you about change in GPE is actually equals to mg delta H, okay? So from here, let's just consider this. If your mass and G is constant, that will mean that change in GPE is proportional to your height change. So if you were to plot a graph of, say, change in GPE over height, it should be a straight line graph that passes through origin. Okay. Second one, if you say something else being constant here, not mass, if you say delta H and G is constant, that will mean that change in GPE is proportional to mass. Okay. So here, if you want to plot out a graph of, say, change in GPE versus mass, again, it will be a straight line graph that passes through origin. Okay. Because what you learned from mass was something like this before, right? Where you say that if y is proportional to x, you plotting a graph of y versus x would give you a straight line graph that passes through origin. You're applying it right over here for both these cases. Okay, this is just for GPE. Now, what about the case where you're talking about KE? Now, KE is half mv squared. So here you consider two cases. You make mass constant. For example, if mass is constant, KE is proportional to v squared. So now, this one, if you were to plot a graph of, say, KE versus V, it will be a curve like this. Okay, same thing as before. If you have gone through your maths course, they will have told you that if y is proportional to x squared, maybe it's better if I just draw it here. If you have y proportional to x squared, you drawing a graph of, say, y versus x will be a curve. But if you were to plot a graph of, say, y versus x squared, it will be a straight line graph through the origin. Okay, so this is something that you would have learned from maths also. If something is proportional to something square, you plotting that quantity versus that quantity will be a curve. But if you plotting that quantity versus that quantity square, you will get a straight line. So here, I can actually have this graph here if I plot KE versus V. Okay, but if I plot KE versus V square, I'll get a straight line graph now. All right, but That one is actually not inside my answer choices, so I'm not going to draw it out. Okay, second case. If your mass is not constant, but this time your velocity is constant, your velocity is constant, your velocity is constant now would mean KE is proportional to mass. So now if you now draw out your graphs, we'll say KE versus M, you by right should get a straight line graph through your origin, something like this. Okay, so now which one is actually the correct one in your current question? So you look at A, mass for different objects moving at the same speed, and then Y is kinetic energy. The x-axis is mass for different objects moving at the same speed, and then Y is kinetic energy. This one is actually wrong. Okay, if you're talking about if you're talking about A should have been this one. This is the graph for A. Okay, because they say mass for different objects moving at the same speed, that means V is constant, only mass is changing. So A should have been this graph. Then you look at answer choice B, speed for an object of constant mass. And then the other, this is for kinetic energy. So here, this one is constant mass. That one is referring to this case here. So speed for an object of constant mass, the kinetic energy would be this. This one is actually B. Okay. You will notice that it's actually matching your graph shape here. So answer is actually B. But then you can actually check with the rest of the answer choices now. For C is change in GPE. This is vertical distance fallen for object of constant mass. This one is talking about constant mass. It's talking about this one here. So this is actually the graph for C. And after that, the last one is again change in gravitational potential energy, but this time they say mass for different objects falling at the same vertical height. That one is saying that delta H is constant. So this is the graph for D. Okay. So A, C, and D all should be giving you a straight line graph through origin. But the graph that is given in the question is a curve. The only one that matches that is this. Okay. So answer is B. Okay, so if that's okay, then I move on again to the next one. So I'll clear this one up. Okay, so question 20. Question 20 is pretty straightforward. You have a steel wire that has a length of 300 centimeter and cross-sectional area of 0.5 millimeter square. The Young modulus of steel is 2 times 10 power 11 Pascal. One end of the wire is attached to a fixed point, a load of 10 Newton is hung from the other end, and the wire obeys Hooke's law. What is the extension of the wire? So this one, you can probably just kind of simply draw one diagram out just to see. This is your wire. You have a force of say 10 Newton being applied here, like this. Okay, they want you to find out what is the extension given all the other values here, where they tell you that the length is actually 3 meter, and then your area is 0.5 millimeter square. Okay. So use Young's modulus equals to ratio of stress to strain. Stress is force per unit area, strain is extension over length, giving you FL over AE. They want extension, so you rearrange your equation, giving you FL over A times Young's modulus. So from here, just sub in your values. Your value is 10 Newton, your length is 3 meter, your cross-sectional area is 0.5, but remember that this is in millimeter square, so change it to meter square times 10 power minus 6 times your Young's modulus of 2 times 10 power 11 you will eventually get your answer as 3 times 10 power 4 meter. Okay, so answer is this. So how do you change millimeter square to meter square? This one, let me just quickly review it for you. 1 millimeter square is the same as 1 millimeter inside a bracket square. You sum in the value for 1 millimeter is 10 power minus 3 meter inside the bracket square. So you eventually get 10 power minus 6 meter square. That's how I got the value 10 power minus 6 here. All right. Okay, so that is question 20. Then we move on to question 21. All right. Okay, so question 21 is deformation of solids already. Now in question 21, the extension of a copper wire is measured for different forces applied to the wire. A graph is plotted to show the variation of the force on the wire against extension, and the maximum force is applied at point P. Which statement must be correct here? Okay. So here, there are certain things to note, certain points to be aware of. There is this point called limit of proportionality, the LOP. And I'll just give it a short form, LOP. Limit of proportionality, LOP, is a very special point where you say is the point to which Hooke's law is still obeyed. Okay, so up to this point, force is directly proportional to extension. The graph is still a straight line. Okay, so these are some things to learn, to remember about limit of proportionality. Is the point to which Hooke's law is still obeyed. Up to this point, your force is still directly proportional to extension. Your graph will still be a straight line. Okay, and then the second thing to learn is this, your elastic limit. This one is, let's just say I call it EL. Your elastic limit is the point to which deformation is elastic. Beyond this point, deformation is plastic. Okay, so there's a relation between limit of proportionality and elastic limit. That one being that elastic limit is usually after your limit of proportionality in the graph. Okay, usually elastic limit comes after limit of proportionality. It doesn't come before. Okay, so with that in mind, let's just look at a few answer choices that you have here. Now, A, they say point R is the limit of proportionality. You see R is here, right? Notice that this portion has started to curve. This part is curved. So therefore, F is not proportional to X anymore. F is not proportional to X. Hooke's law is no longer, Hooke's law is no longer applied here. Hooke's law is no longer obeyed. Hooke's law no longer obeyed. Okay, so this one is out. Okay, the most obvious giveaway is that you can see that it's curved. The moment you see it's curved, it is already no longer obeying Hooke's law. Okay, so A is out. And then you look at B, the elastic potential energy of the wire at point S is given by the area under the graph between points T and S. So basically they say that at point S, the elastic potential energy is actually given by this. Here they say EPE is the area under the ground. This one is correct because you already learned this in your deformation of solids before. Strain energy is actually the area under your Fx graph. So they say at point S, the energy stored is the area between T and S. This is T, this is S. That one is actually your strain energy. So B is correct. Okay. And then after that, you look at answer choice C. There is no plastic deformation between points Q and P. Okay, points Q and P is this one. Maybe I better just highlight in black. They say no plastic deformation. Now, in the first place, you probably have already exceeded the elastic limit. You see, you can probably say this. Either R or Q is the elastic limit. Beyond that point, deformation is plastic. So them saying that between Q and P, deformation is elastic, this is actually wrong already because you definitely would have exceeded your elastic limit already. So C is out. And then after that, you look at the last answer statement. This one, they mentioned that the wire obeys Hooke's law up to a point between R and Q. This one again is wrong because you can see it's still curved. So F is not proportional to X. Hooke's law is no longer obeyed. So D is also out. Okay. So only correct answer is actually B right over here. All right. So that one is for this. Then after that, we look at waves. There's one question here. Okay, maybe I can just do this question before we call it a day. This one is on waves. Now you look at question 22, they told you the variation with distance x or the displacement y of a transverse wave on the rope is as shown at time t equals to 0. The wave has a frequency of 0.5 Hertz. A point P on the rope is marked. The diagram shows you the original position of P and 4 new positions. What is the position of P at time t equals to 1 second? Okay. All right, number one, this is not a stationary wave. Okay, it's a progressive wave. Progressive transverse waves specifically. Progressive transverse waves transfer energy, but not matter or mass or particle from one end to another. Okay. Progressive transverse waves do not transfer particles, they don't transfer mass, they don't transfer matter from one end to another, they transfer energy. Okay. So for the particle P here, or point P here that they've indicated to you, as your wave travels towards the right, particle P isn't going to travel along with it. It won't move along with the wave. All it'll ever do is that it'll just oscillate up and down like this about its equilibrium position. It will just oscillate up and down about its equilibrium position. Okay. It won't travel towards the right. It will just oscillate up and down about its equilibrium position. Okay. And when it oscillates up and down, it will have a certain period. Okay. So what I can say here is that any particle on the wave will just oscillate about its equilibrium position. Okay, so particle P will just oscillate about its equilibrium position, and then after that it will have a certain period associated with its oscillation. So in my case, they already told me my frequency is actually 0.5 Hertz, right? So I can actually find out the period from there. The period is the reciprocal of my frequency, so it's 1 divided by 0.5, giving me 2 seconds. Okay, so my particle P is right over here. At t equals to 0. Okay, so if it were to oscillate one complete cycle, it would have moved from here, go down, and then go back up. This is one cycle. This is 2 seconds. Okay, so the question wants the position of P at 1 second. So from there, you can actually break out your oscillation into 2 separate parts. Actually 4 separate parts now if you wanted to. Let me just try and draw it out. If this one was your particle P, I mentioned to you that it will just go down and then go up. This is one cycle. But that same oscillation, you can actually break it out into 4 separate parts. This is the same particle P. You can break it out into one part like this, another part like this, another part like this, and another part like this. It can be broken up into 4 separate parts. Okay, these 4 separate parts add together will still give you one cycle. So if one cycle you know is 2 seconds, if you broke it up into 4 separate parts, this one will be 0.5 seconds, 0.5 seconds, 0.5 seconds, and 0.5 seconds. So if the question asks you for 1 second, it's actually really just this one and this one. So at t equals to 1 second, your particle is actually going to be here. Okay, this one was t equals to 0. This is now t equals to 1 second. You will be at position B. Okay, so question 22, answer is B. All right. Now in question 23, you have a cathode ray oscilloscope that is connected to a microphone which detects sound or constant frequency. The trace on the screen of the CRO is as shown here. Which property of the sound wave is measured using only information from the CRO? So what can you determine only by looking from the CRO here? So this is your typical waveform trace on the CRO. Usually from looking at this waveform, you can easily say that this part here is going to be your period T, and then this part here is going to be your amplitude A. Okay, so you look at the answer choices, what can you determine using only information from the CRO? It seems to be amplitude is in, period is in, and then when you're talking about speed and wavelength, these two are obviously out because you cannot see them directly from your CRO measurements. You actually have to use a specific equation to calculate them out. Namely, you have to use V is equals to F lambda. So you will need to get your lambda from somewhere else, your frequency from somewhere else, before you can even find your speed. Okay, so for speed and wavelength, you cannot actually get it directly from your CRO, but amplitude and period you can. But now there's an issue where you seem to have two possible answers. In your case, amplitude is actually not correct here. Period is the one that you can actually get directly from your CRO. Now, why you say that you cannot say amplitude is your answer here is because by right, amplitude is max displacement from equilibrium. So this is the definition of amplitude, where it's max displacement from equilibrium. The unit of max displacement, or rather amplitude, should be in meters, isn't it? So when you're reading your amplitude from your CRO here, yes, it is amplitude, but it's a different unit altogether. The unit here for your amplitude from the CRO, the unit here is actually in volts. So not meters. If you are getting the amplitude value in terms of volts, you will eventually need to convert it to meters. So you are not getting the property of sound wave using only information from the CRO. You still need to do some sort of conversion. Okay, so that's why the answer A here is wrong. B is the correct one. Okay, then if you're okay with that, then have a look at question 24. You have a transverse wave and a longitudinal wave both traveling in the same direction down a long stretch spring. Which statement is not correct for these two forms of wave? You're supposed to pick a statement that is incorrect here. So in your case, the statement that is incorrect, you probably should try and draw the waves. Just give me a while while I try to draw the waves for you. You have two types of wave, longitudinal and transverse. So if I mention to you transverse wave, and then I mentioned that your particles are something like this, you have a row of particles, and your wave direction is, say, right over here. This is your wave direction. The direction of oscillation of your particles for a transverse wave will be in this manner, right? Okay, perpendicular to wave travel. This is what transverse wave actually is. Then if you're talking about longitudinal wave, again, let's just say you imagine that there's a row of particles here, and then this is the direction of your wave travel. The direction of oscillation of your particles for longitudinal waves will be like this, right? Parallel to wave travel. Okay, so that is what you will have understood. You now look at the answer statements one by one. The displacement measurements for the particles of the two waves are made at right angles to each other. So this is actually true. This is actually correct. Okay. How you measure your displacement for these two waves are actually at right angles to each other. You see, in your case, for transverse wave, you're making your measurements vertical like this. But when you're talking about longitudinal wave, you're making your measurements horizontal like this. They are both perpendicular to each other. So answer statement A is actually correct. Then you look at answer statement B, the energy transferred by the two waves is in the same direction. This is actually also correct, because here your wave direction is also the direction of your energy transfer. Okay. So in your case here, when they say to you the energy transferred by the two waves is actually in the same direction, this is actually also correct, because energy transfer is in same direction as wave travel. Okay. And then if you look at answer statement C, the velocities of the two waves are in the same direction. This is also kind of true. Your wave direction is both going towards the right. Your velocity is also going to be towards the right. So answer statement C is also correct here. All right. So that leaves you with the last statement being the incorrect one. So let's just review this. The wavelength measurements for the two waves are made at right angles to each other. Now, you consider this. What is the definition of wavelength in the first place? Wavelength is actually the shortest distance between 2 points that are in phase with each other. So shortest distance between 2 points that are in phase with each other could be shortest distance between adjacent crests. Okay, so in our case here, for both a transverse as well as a longitudinal wave, if I wanted to find out the wavelength from them, I will have to just look at the distance between adjacent crests. Okay, so in my case, I could probably say that these 2 points here are my crests. So this one is my wavelength. Similarly, I can also say that these 2 points are my crests. So this one is also my wavelength. So the direction in which I measure the wavelengths is actually the same. You see, I'm trying to measure horizontally across these 2 points. This one is also measured horizontally across these 2 points. So here they say wavelength measurements for the two waves are made at right angles to each other. This is actually the wrong one. They actually measured along the same direction. So answer here would be D. Okay. So that's for this particular question. Then let me clear this one off and move to the next one. Okay, so in question 25, you have a man standing next to a stationary train that hears sound of frequency 400 Hz emitted from one of the train's horn. The train then moves directly away from the man and sounds its horn when it has a speed of 50 meters per second. The speed of sound in the air is 340 meters per second. What is the difference in the frequency of the sound heard by the man on the two occasions? Okay, so just consider this. You have a case where your source was stationary. So I can imagine that this one is my source. And then this one is my observer here. Both are stationary right now. So in my case here, the train, or rather my source, is emitting sound of frequency 400 Hz. So my frequency of source here is 400 Hz. Okay. Then whatever I hear here by the observer will also be 400 Hz. You do not have Doppler effect here yet because there's no relative motion between the source and the observer. So whatever the train is emitting will also be the same thing that the observer is hearing right now. Okay. So then after that, they mentioned that your train is actually moving. This time your train is moving away from the observer, moving away from the man. So moving away from observer would be a case where you have the observer now here, but the train, or rather the source, is moving away. And the source is moving away with a speed of 50 meters per second. So for the case where you have a source moving away from the observer, the thing that we always remember is that the observed frequency will be less than your source frequency. Okay, so in your case, you will need to use equation F0 equals to VW over VW plus PS times Fs. This one will give you your observed frequency right now. So in your case, if you just sub in the values that you know, the observed frequency would now be VW. VW is the speed of the wave is 340 over 340 plus the speed of the source, which is 50 meters per second, times your observed, multiply with your source frequency of 400 Hertz. You will eventually get the answer as some value. Just let me see the workings here. You will eventually get your answer as 349 Hertz. Okay. You will eventually get the answer as 349 Hertz. Let me just write all these values out properly for you. This is 340, giving you 349 Hertz. Okay. So the question wants the difference in frequency of the sound heard by the man on the two occasions. In your case, before the train started moving, this was your observed frequency. But now after the train has started moving, your observed frequency has actually changed to 349 Hertz. So what you really want is the difference in the observed frequencies now. So here, your delta F, the difference in the frequencies will actually just be 400 minus 349, giving you an answer of 51 Hertz. So your answer here would just be A. Okay, so that's for question 25. Now for question 26, which list of regions of the electromagnetic spectrum is in the order of increasing wavelength from left to right? So they want your wavelength in increasing order. So you have to reproduce your EM wave spectrum here. So I think I mentioned to you guys before for paper 1, there's always that 1 or 2 questions where you will always need to reproduce your EM wave spectrum. It's only by reproducing it will you be able to answer your questions. So you usually start off with drawing a series of vertical lines for the EM wave spectrum. And then after that, you start with some values, 10 power 3, reduced by 10 power 3 each time. So it becomes 10 power 0, 10 power minus 3, 10 power minus 6, 10 power minus 9, and 10 power minus 12. Okay, there's one odd one here where between 10 power minus 8 and 10 power minus 9, you have to put 10 power minus 7. This is because you have to take into account visible light. Because wavelength of visible light is from 400 to 700 nanometer, which is actually 4 to 7 times 10 power minus 7 meter. That's why you have a 10 power minus 7 here. Okay, so once you have drawn those lines out, you just need to fill in the blanks. Raging Martians invade Venus using X-ray guns. Okay, so the first letter of each word is actually representing your wave. Radio waves, microwaves, infrared, visible light, ultraviolet, X-ray, and gamma rays. So here, once you've drawn out the spectrum, going towards the right is where wavelength is decreasing. So if you go towards the left, that is where your wavelength is increasing. You're actually supposed to look towards the right currently. Sorry, you're supposed to look towards the left right now because you want to see in order of increasing wavelength. So the answer will actually just be A itself. Because you see from gamma rays, you go to ultraviolet, and then you go to infrared. This is really an increasing order of wavelength. If you do your analysis for B, C, and D, you will eventually notice that there's one that's in the wrong order. Okay, so this is for question 26. And then you move on to question 27. Now, question 27 mentions that the principle of superposition states that a certain quantity is added when 2 or more waves meet at a point. What is this quantity? So that one should have been displacement. Okay. A close answer would be amplitude, but amplitude is actually not the correct one because if you try to recall what principle of superposition actually is, principle of superposition actually says this. When 2 or more waves meet at a point, when 2 or more waves meet at a point, the resultant displacement is the sum of the individual displacement, displacements due to each wave at that point. And that's what principle of superposition actually is. You are really talking about the resultant displacement being the sum of individual displacement due to each wave at that particular point. Okay, so the answer is rightly going to be B. Okay, they are not talking about amplitude. Neither are they talking about intensity nor wavelength. All right, so this is question 27. Then I move on to question 28. Okay, question 28 would be something that's a bit different than the ones that you've always done. Now, in question 28, they mentioned that a stationary sound wave is formed in a gas-filled tube of length L, which is closed at one end by a piston. The length of the tube can be altered by moving the piston. The length of the tube and the frequency of the sound are varied so that the stationary wave always has two antinodes and two nodes as shown here. The graph shows you the variation of the frequency f of the stationary sound wave with length L of the tube. What is the speed of sound in the gas in the tube? Okay, so here, bear in mind that they are actually changing the length of the tube and the frequency at the same time. Okay, the ones that we've always been doing up to now was either length is fixed but frequency varied, or it's the other way around where we tell you that f is fixed but length is varied. The current one that you're having is L and F varied at the same time, eventually giving you a graph that looks like this. Okay, this is the frequency and the length that they use that gave you a stationary wave that always has two antinodes and two nodes. Okay, so from here you're supposed to determine the speed of the sound inside the gas. Now this one you can actually just straight away use V is equals to F lambda. If you already know the wavelength and the frequency, you could easily find out your speed here. Okay, how do you get the frequency and wavelength first in the first place? You can actually get it from the graph. So to get these two values, what you just need to do is find from one point on the graph. Rather than saying one point, maybe it's better to say find from any point on the graph. Find from any point on the graph. You can find f and lambda from any point on the graph. So in my case, let's just say I want to find it from this particular point. Okay. So if this is the particular point that I am interested in, what is the value of my frequency is 500 Hertz. What is the value of my length? You will notice that this is 5 boxes for 5 centimeter, right? So one small box here will actually just be 1 centimeter. And then you will notice that this one is actually right in the middle of one small box. This one will actually have been 4.5 centimeter. Okay. So here, how are you going to do this? You just look at what the question said earlier. For any of the points that you have on this graph here, the stationary wave that is formed always has two antinodes and two nodes. Okay. So whatever frequency value or length that you have, you will always be getting this stationary wave inside. Okay. Now from here alone, you can actually deduce out the wavelength, because you see, one of the things you have learned about stationary wave is that distance between adjacent node and antinode is equal to quarter wavelength, right? I'm not talking about adjacent nodes or adjacent antinodes. I'm talking about adjacent node and antinode. Okay, so you're talking about adjacent node and antinode is going to be quarter lambda. So here you should have quarter lambda here, and then this one will be quarter lambda, and this one will also be quarter lambda. So for this full length L that you have, you actually have 3 quarter lambdas. So 3 quarter lambdas equals to L. Lambda will actually be 4L over 3. So look at the point that you have chosen. The L is actually 4.5 centimeters. So here I can actually say that it's 4 times 4.5 divided by 3, giving me some value of 6 centimeter. Okay, I'm getting a value of 6 centimeter. So now that I have my wavelength, I also have the value of my frequency. I have these two values now. I can actually sub them into my equation, V equals to F lambda. So this one will be 5,000 times with the wavelength of 6 centimeter, change it to meter. You will get your answer as 300 meter per second. Okay, so your answer here is C. Now you could likewise repeat your calculations for any point on the graph. It could be that maybe you want to use this point, this point, this point, or this point. You can, okay? Any point you choose would give you an answer that's close to C. All right, in my case, I choose the first point because it's the most convenient one to use. All right, so that one is question 28. Then I move on to 29. All right. Okay, now for question 29, this one relates to diffraction. So over here, they mentioned that the diagram shows the diffraction of water waves in a ripple tank as they pass through a gap between two barriers. Which diagram here is correct? Okay, so there's basically two things to note here when it comes to diffraction. Wavelength does not change after diffraction. Okay, wavelength should not be changing after diffraction. Okay, it does not change after diffraction. And then after that, the second thing to note here is this. Significant diffraction occurs when gap width is comparable to wavelength. Okay, significant diffraction will only occur when the gap width is comparable to wavelength. In other words, it's referring to something like this now. Your gap width must be less than or equals to your wavelength in order for significant diffraction to occur. If your gap width is equal to your wavelength, you will have significant diffraction. If your gap width is slightly less than your wavelength, you will also have significant diffraction. So these are the two things to note when it concerns diffraction. Now, your answer here should have been B. All right. Because what you notice here is this. This is your wavelength. You see, this is before diffraction. After the diffraction, notice that your wavelength is also still the same. You can actually imagine that these are actually your wave crests. These are actually your crests. So the distance between two wave crests is actually your wavelength. Okay. So if you just look at criteria number 1, where wavelength does not change after diffraction, this will have automatically told you A, C, and D is out. Because if you just look at how the spacing of the lines, or rather the distance between the crests are after diffraction, they are actually not the same. See, for A, it was like this before diffraction. Then after diffraction, it became like this. The wavelength has suddenly dropped. And then if you look at C, this is your wavelength. After diffraction, it is now like this. Your wavelength has increased. The same could also be said for D. Your wavelength before this was like this, but then after your diffraction, it suddenly became smaller. So based on the first criteria itself, you have already eliminated A, C, and D. Only B seems to have the same wavelength. And then after that, you can also double check with criteria number 2. Significant diffraction will only occur if your gap width is comparable to your wavelength. So here, look at your gap width. Your gap width is this one. It's almost similar in size to your wavelength. So it is reasonable to assume that you have significant diffraction. This is to be expected. Okay. So answer is B here. Then if you're okay with that, then I'll move on to question 30. So clear off everything on the screen. Okay, now for question 30, you have a beam of light from laser that is incident normally on the double slit. Interference fringes are seen on the screen placed parallel to your double slit. The separation of the two slits is A, the distance between the slits and the screen is D, and then the distance between the centers of the two adjacent bright fringes is X. D and A are both half. What will be the distance between the centers of the two adjacent bright fringes after these changes? Okay, so for your case here, this one, since they mentioned that this is a double slit, the equation that should always come to mind is this: lambda is equals to AX divided by D. Now they're talking about what happens to the distance between adjacent bright fringes. You're interested in X now. So X is lambda D over A. So D and A are the ones that are being changed. There's no mention of wavelength being changed, so you can assume that lambda here is constant. So lambda is constant. Therefore, X is proportional to D over A. Okay. So there's two ways to go about this. The first way is just by looking at this simple ratio here. So if in my case, I know that D is half, that means D reduced by 2 times, X by right will reduce by 2 times because X is proportional to D here. Then if I look at A is reduced by 2 times. X must increase by 2 times because here X is inversely proportional to A. If A decrease, X must increase. And because they are both at power 1, the amount of change is actually the same. A reduced 2 times, X must increase by 2 times. Okay, so here you notice that if you talk about D, X reduced 2 times. If you talk about A, X increased by 2 times. So the effects kind of cancel each other off. So overall, you can actually just say this. Overall, X is unchanged. So the answer should have been B. Okay, there's no change in your fringe spacing. But you can also do it another way. This one is by actually subbing in some values. So this one is method 1. Method 2 will be you actually trying to sub in some values based on the relation that you have just derived here, where you can probably say something like this now. X2 to X1 is the same as D2 over X2, sorry, D2 over A2 over D1 over A1, giving you D2 over D1, A1 over A2. So from there, if you try to sub in your values, D2 should be half of D1, then A2 should be half of A1. And then X1 is actually just X itself. Okay, so here you will notice that they all kind of cancel each other. D1s will cancel, A1 will cancel, the half will cancel off. Eventually, your answer will just be X2 equals to X, which is answer choice B. Okay, this is another different way of doing this. Okay, so this is okay. Then I move on to question 31. Okay, now in question 31, you have a beam of light of wavelength 400 nanometer that's incident normally on the diffraction grating that has 300 lines per millimeter. Light passes through the grating and produces a series of maxima which are observed on a similar circular screen as shown. What is the total number of maxima observed on the screen? So keyword here is total number of maxima, or total number of bright dots that you can observe on the screen. So here, if say this one is your light of wavelength 400 nanometer, it hits the diffraction grating, you know by now that it will just split into a few different beams like this. Okay, where you would say that the center bright dot or central maxima is 0 order. Then after that, it will be first order, second order, on either side of your center maxima. Okay, so this is what you expect to see. So if you want to find out the total number of maxima, you need to find the maximum order number in the first place. So since this is a diffraction grating, d sine theta equals to n lambda, and n is max when theta is 90. So you sub in the values, d sine 90 equals to n max lambda. N max would actually just be the ratio of d over lambda. Okay, so but before you can go through that, you need to find out the value of d. The value of d is not given here. They merely gave you this information where they say that your diffraction grating is 300 lines per millimeter. This is actually n, number of lines per unit length. Okay, the relation between d and n is this, where you say d is 1 over n. So here you're basically taking 1 millimeter divided by 300 lines. This will give you an answer in millimeter. D now is in millimeter. Okay, but you want to change to meter. So you will need to multiply with 10 power minus 3 in order to change it to meter, because 1 millimeter is 10 power minus 3 meter, isn't it? So you need to change from millimeter to meter. You multiply with 10 power minus 3. So once you have that, you can now work with the values to find n max. This is 10 power minus 3 divided by 300 divided by wavelength of 400 nanometer. You will eventually get your answer as 8.3. Okay. So this value here, 8.3, you either take integer value only, or you just round down. Okay, this is always either of these two. So therefore, your n max is going to be 8. Now from here, you want to find the total number of maxima, right? So if you want to find total number of maxima, it will be 2 times of n max plus 1. So it will be 2 times 8 plus 1, giving you an answer of 17. Answer here is D. Okay. So why is it multiplied with 2n max? Is because on either side of your central maxima, you have the order numbers repeating themselves, right? It repeats themselves twice because there's 1 on each side of your center maxima. And then after that, why is there plus 1 here? It's because you need to take into account the central maxima. Okay, so that's for question 31. Then we move on to question 32. So let me clear this thing off. Okay, now in question 32, 2 wires X and Y are made from the same metal. The diameter of wire Y is twice that of wire X. Wire X, wire Y, and a battery are connected in series. What is the ratio of the average drift speed of free electrons in wire X to wire Y? Okay, so let's just try to draw your circuit here. Your circuit here is where you have wire X and wire Y connected in series. Let's just say it's like this. This one is X, this one is Y. Okay, so since they mentioned drift speed here, when it concerns drift speed, there's always one equation that you would be using, that one being I is equals to AN QV. And then after that, your area can actually be expanded to become pi over 4 d square and QV. Okay, so you want to find ratio, you would use this equation right over here, but there are certain things that you need to determine to be constant here. All right, first thing first is that they say it's same metal. Same metal would mean same resistivity. Sorry, same metal here would mean same number density, not just same resistivity, same number density. Okay. And then second thing here, they mention they are connected in series. If your wire X and Y are connected in series, when current flows out of your battery and flows to X and Y, it's actually the same current flowing through both of them. So I can actually say that you also have same current. Okay. And the last thing to note here is that they mention brisk speed of free electrons. So you're talking about electrons, the charge of electron is also always going to be the same, which is 1.6 times 10 power minus 90 coulomb. So you also have same Q here. So these are the three things that should be constant for wire X and Y. From here, you can now work out this relation. I, N, and Q constant. Therefore, V is inversely proportional to D squared. This is the relation that you have. So now, if I want to find out the ratio of brisk speed of X to Y, you can now say something like this. Vx to Vy is actually the same as 1 over dx squared over 1 over dy squared, giving you dy squared over dx squared. So Vx to Vy is now dy squared to dx squared. The diameter of y is twice that of x. So here you will actually say that dy is 2 times of dx, square it, dy by dx squared. So remember to square for the 2 and the dx, you eventually get 4 dx squared. So you will end up with 4 to 1 for ratio of Vx to V1, for ratio of Vx to Vy. So the answer here would rightly be D. Okay, so this is again based on the first method of doing things. But again, if you try to do this based on the second method, just by using simple ratio, V is inversely proportional to D squared. If I just look at for wire X now, they say that diameter of Y is twice the wire X. That means wire X has half the diameter of Y. Okay, so if you look at from the point of view of wire X, the diameter is actually half that of Y. So D is reduced by 2 times. Therefore, V is increased by 4 times. Why is it reduced? Because V is inversely proportional to D. Why is it 4 times? It's because there's a square term for D. Your change is squared. All right. So from here, you will then get this relation out where we can say that Vx is therefore 4 times of Vy. So that Vx to Vy is going to be 4 to 1, which is again the same answer at D. Okay, so that's for this one. Then you move on to question 33. Now you have a resistor or resistance R. When the potential difference PD across the resistor is V, the current in the resistor is I. The power dissipated in the resistor is P, and work W is done when charge Q flows through the resistor. What is not a valid relationship between these variables? Okay, so pick the equation that is actually wrong here. Now, if you already remember your equations on current electricity out, these are some of the equations that you should have remembered by now. If you're talking about power, power is P is equal to VI, is I squared R, is V squared over R. And then when you're talking about voltage, voltage is work done per unit charge. This is what you get. So you look at the answers one by one. A would be correct because it comes from P equals to VI. And then B will also be correct because it comes from V equals to W over Q. Then you look at C, C will also be correct because it comes from P equals to I squared R. Now you look at D, D is not correct because this one by right should have been from P equals to V squared over R. They're missing a square for the V here. So answer here is D. Okay. So that one should be all right for this particular question. Okay, so if this is okay, then I move on to another next question, question 34. So for question 34, this one concerns some sort of graph. Okay, so let me just zoom in a little from here. Okay, now here they mentioned that you have a fixed resistor and a filament lamp that are connected in series to a power supply. The IV characteristics for the two components are shown. The current in the fixed resistor is 0.34 amps. What's the resistance of your filament lamp right now? So same thing like one of the questions before this, they mentioned to you that your two components, the fixed resistor and filament lamp, are connected in series. So you try to draw the circuit, it actually looks something like this right now. You have a fixed resistor and you have a filament lamp like this. And there's going to be current that flows through them. Okay, like this. This is current I. Okay, so the question wants you to find out the resistance of your filament lamp. They want you to find out the resistance of this filament lamp based on the graph that has been given to you. So one thing that you should have been able to realize from looking at this diagram that's just been drawn here, if you're talking about the current through the resistor and the current through the lamp, because they are connected in series, the current through your resistor will be the same as the current through your lamp, which in your case is going to be 0.34 ampere. It's already given inside your question. Okay, and then after that, if you look at the graph for filament lamp, from filament lamp graph, from the filament lamp graph, try to find out the voltage corresponding to a current of 0.234 amp. From filament lamp graph, when I is 0.34 amps, your voltage is going to be some value. So let's just try and see where it is. 0.34 is somewhere around here, if I'm not mistaken, because it's 0.1 divided by 5 squares. So each square is actually 0.2. So now if I want to get 0.34, it will be 2 small squares from 0.3. And then after that, the corresponding value of my voltage would be here. Okay, so this one, I see that there's 2 divided by 10 boxes. So each small box is 0.2. This one therefore must be 4.2 volts. This one was 0.34 amps. Okay, so let me just write it out here. So you will get a voltage value of 4.2 volts. Now from here, you can now find out your resistance, because resistance is the ratio of PD to current. So you take the values of voltage and current through your filament lamp right now. You take 4.2 divided by 0.34. You will eventually get the answer as 12.4 ohms. Okay, you get the answer as 12.4 ohms. The answer here would actually be B. Okay, so that's for this particular question. Okay, so if that is okay, I again move on to another next question. This is now question 35. So let me clear this thing off. Okay, so for question 35, you have a piece of conducting putty, modeling clay, or constant resistivity that is formed into a cylindrical shape. The resistance R between its flat ends shaded is measured here. The same volume of putty is reformed into cylinders of different lengths L, and the resistance R between the flat ends is measured for each value of L. Which graph best shows you the variation of R with L? Okay, So certain things to note here is that they mention you have constant resistivity, okay? And then the same volume of putty is being reformed into different cylinders of different lengths and different resistances. So here they want you to find out the variation of R with L. Since you're talking about R and L now, this equation would always be used. R is equals to rho L over A, okay? Now you cannot use this equation directly as it is, because here you see that resistivity is constant, right? The thing that is changing now would be your L. This one varies, as well as your A. Your A will also varies, okay? So right now you need to get rid of this A here right now, because A here is not constant. So if A is not constant, what's the relation of A with L right now? You can actually work out another separate relation here where you say that the volume is actually area times length. Because if you look at this cylinder, you have area A and you have length L, right? So your volume is actually equals to area times the length. Now they mentioned to you that you are using the same volume of putty when you're reforming the cylinders. So V is constant, therefore A is inversely proportional to L. When your length increases, your A would drop, and vice versa. So now that you have this relation here, and you try to put it inside this equation right over here, you can actually say something like this. Let me just try to write all the workings. Because I really know that this is constant resistivity in the first place, I can say that rho is constant. So R is proportional to L over A. But at the same time, I really know that area is inversely proportional to length, right? So if I try to combine these two together, I'm going to get a new relation where I can say this. R is actually proportional to L squared. Okay? So this one here, I try to put it inside here. I will get R proportional to L squared. So when it comes to plotting a graph of R versus L from the question here, what I'm supposed to get is going to be a curve that looks like this. The answer is supposed to be D, okay? Now, there's something that you will have learned from maths before this. If I tell you y is proportional to x, and I ask you to draw a graph of y versus x, you would have immediately said that it will be a straight line through the origin, okay? Now, if I then tell you y is proportional to x squared, there are two specific graphs that you can draw out of this. The first one is y versus x, and another one is y versus x squared. If you're being asked to draw a graph of y versus x, you're supposed to get a curve that looks like this. But if I ask you to then draw a graph of y versus x squared, this one will give you a straight line graph through the origin, okay? So this is something that you will have learned from maths when it comes to certain relations and the graphs associated with it. So this one is actually this one here. And then they're asking you to plot a graph of R versus L, right? You're looking at this graph. Okay, so that's why the answer is actually D here. All right. So that is for this particular question. Then after that, let me just go on to question 36. Question 36 is actually a very simple one. So I'll clear off the diagram here. Okay, now in question 36, they mentioned to you that the diagram shows the symbol for a component that may be used in an electrical circuit Which component is represented by this circuit symbol? Okay, so this question is really just about you knowing what circuit symbols represent what component. Questions like this actually have almost always never come out, but somehow is coming out for this current year. So you have 4 different answers: buzzer, electric bell, loudspeaker, and microphone. This one, you would need to remember the circuit symbols. Okay, the answer here is actually buzzer. Buzzer would be this one. This is the symbol for buzzer. But when it comes to an electric bell is actually the other way around. It looks like this. This one is an electric bell. This one is for electric bell. Okay, an easy way to remember which one is going to be buzzer, which one is going to be electric bell, because you see the symbols look similar, right? The only difference is that this one seems to be pointing down, this one seems to be pointing up, right? So the best way I can somehow remember which one is going to be buzzer, electric bell is that since I remember that this is a bell, I try to visualize the shape of a bell. The shape of a bell is something like this, right? So I know that, yeah, it's going to be something like this. All right. So electric bell is like that. Now loudspeaker is going to be something like this. This is loudspeaker. And then for microphone, it will be something like this. All right. So this is the respective circuit symbols. The respective circuit symbols for all other components, you can actually get it from your syllabus booklet, or you can actually get it from the notes that I gave to you guys a long time ago. Under DC circuits, the first page, this is actually taken from your syllabus booklet. All the other common circuit symbols for certain components are actually written there. Okay, so that's for that. Okay, now is 5:11 p.m. Let me just give you a 10 minutes break at 5:21 p.m. I'll be able to finish this paper before the class ends, so I might probably move on to a next paper, or I could actually try and discuss the earlier questions. You just let me know which one do you prefer. Okay, after the break, it's either I go and discuss question 1 to 22 for you guys in this lesson, or I go and do February, March 2022 for you guys. Okay, you let me know after the break or after I finish the question later. Okay, so let's just take a short break. Okay, now for question 37, which rule correctly describes Kirchhoff's laws? So when you're talking about Kirchhoff's laws, there's only 2. Kirchhoff's first law is talking about the sum of currents going into a junction is equal to the sum of current going out of a junction, and it's based on the principle of conservation of charge. When you're talking about Kirchhoff's second law states that the sum of EMF is equals to sum of PD in a closed circuit loop. This is actually a principle of conservation of energy. So the one that fits both of these in your current question is actually just A. Here they said that for Kirchhoff's first law, the sum of currents entering a junction equals the sum of currents leaving the junction, and is based on principle of conservation of charge. And then for Kirchhoff's second law, the sum of the EMF around any closed loop in a circuit equals to sum of the PDs around the same loop, which is based on the principle of conservation of energy. So answer A is rightly the correct one. Then you look at question 38 from there. Now in question 38, they mentioned that you have a potential divider circuit that is formed by connecting a battery of negligible internal resistance in series with 2 variable resistors as shown. The variables resistors have resistances Rx and Ry, and then Vx is the potential difference across the variable resistor with resistance Rx, and Rx and Ry are both changed at the same time. Which combination of changes must cause Vx to increase. You want the one that is going to cause Vx to increase with 100% certainty. Okay, so this is talking about potential divider circuit. Okay, so you have two resistance values there. Which combination is going to cause your Vx to increase? There are three things that you can actually just see from the diagram there. For the circuit that has been given to you, when you look at the current flow that comes out of the battery, current will flow like this, isn't it? This is how current will actually flow. Okay, so one of the things that you can see from here in the first place is this. The I, the current, maybe I better rewrite this. Your current through Rx and Ry is the same, regardless of current value. Okay, your current value could be changing as a result of you changing the resistances, but that doesn't matter. The current that flows through it, that flows through Rx and Ry will always be the same, regardless of whatever current value you have, because of the series connection. Okay, so if you apply V equals to IR for these two resistors, you can say this. V is equals to IR. If I say that I is constant through both of the resistances, that means V is proportional to R. And then from there, I can actually deduce one thing. If your R is to increase, your PD would actually increase, and vice versa. Okay, so in my case, if I want Vx to increase, therefore Rx must increase. Okay, this is number one. Okay, this is the first criteria. This is criteria one. Okay, in order for my Vx to increase, my Rx must also increase. So this is based on what you've done here. And then after that, if you look at another different way of looking at it, if you apply Kirchhoff's second law to your current circuit, specifically you apply it to this particular loop right over here, you could have said that your EMF E is equals to the voltage across your Rx plus the voltage across your Ry. Okay, so now the EMF value itself should by right remain fixed because you did not change out the battery, you did not change out the cell. Okay, and now you also want Vx to increase in the first place. But if your Vx is increased right now, your Vy must drop. Okay, so in order for your Vx to increase, Vy must drop. So let me just write it here. For Vx to increase, Vx must decrease. All right, so not Vx. For Vx to increase, Vy must drop. For Vx to increase, Vy must decrease. So you relate to what you have done right at the top here and relate it to this. Since Vy is dropping, therefore Ry must also be dropping. This one will be criteria 2. So your answer here should have been B. Your Rx must be increasing, becoming larger. Your Ry must become smaller. Okay, so that's for this particular question. Then if you're okay with that, I'll move on to question 39. Okay, for question 39, you have an actinium nucleus that has a nucleon number of 227 and a proton number of 89. It decays to form a radium nucleus emitting a beta minus particle and an alpha particle in the process. What are the nucleon number and proton number of this radium nucleus? So for this particular case, it will probably be better just to draw out the nuclear equation. You have actinium with proton number 89, nuclear number 227. It decays to give you radium by emitting a beta minus particle, -10 here, and an alpha particle, 42 here. Okay, so you need to apply conservation of proton number and nuclear number for your nuclear reaction here. So this one is 89. The bottom one must also be at 89 if you're talking about the proton number. So now I know that this one is -1. This is 2. It's actually just 1. -1 plus 2 will just be 1, isn't it? So how much more should I need here in order to get 89? You will need to have 88, because 88 plus with 1 gives you 89 in the first place. Or you can just think of it as this: 88 minus 1 becomes 87, plus 2 it becomes 89. Same thing. Then after that, you look at your nuclear number is 27. So at the top here, you have conservation of nuclear number. You must get back total 227. So here you have 0, you have 4. How much do you have here to get back 227? This one, you can actually say you would need 223. 223 plus with 4 gives you 227. So your answer here would have been B. Okay, this is the nuclear number and proton number for the radium nucleus. Okay, then last question, question 40. Question 40, which statement is not correct? Find the incorrect statement. Now this one is talking about mesons and baryon and whatnot. So let's just review a little some of the things that we will have learned. When you're talking about meson is just a pair of quark and anti-quark. When you're talking about baryon is a group of 3 quarks. So meson and baryon both belong to another group of particles called hadron. Hadron is just group of quarks. Okay, meson is a more specific hadron, baryon is a more specific hadron in the sense that they tell you how many quarks should you have and what are the types of quark, what are the type of quarks you should have. Okay, so when you're talking about baryon also, they could ask you what are the examples of a baryon. The most common example of a baryon would actually be your proton and your neutron. Because proton is up, up, down, 3 quarks. Neutron is up, down, down, also 3 quarks. So those are baryons too. You are also correct in saying them as hadrons. All right. So you look at your answer statements one by one. A meson consists of 3 quarks. This is obviously wrong already. It should have been a pair of quark and anti-quark. Answer is supposed to be A. But you can actually check with the rest of the answer statements. A proton is a baryon. That is correct because you have up, up, down quark. A quark is a fundamental particle. That is also correct. There are 6 flavors or types of quarks. This is also correct because when you're talking about the 6 flavors or types of quark, you have up, charm, top, then you have down, strange, and bottom. These are the 6 quark types. Okay, so B, C, D is correct. Only A is the incorrect one. All right, so that's it for this paper.